Here's a diagram or a picture of a similar sketch of a similar situation. And we have a pendulum suspended from the ceiling. The equilibrium position of the pendulum is directly below the point where the string is tied. And that position, we call that the equilibrium position. And we're going to call the displacement x. And actually x is going to be a vector. So let me no, I'll leave x as it is, but then down here I'll make the vector x. So x has a direction, and basically the direction is to the right or to the left as we're looking at the system. We have a mass here. M suspended, and we have a mass of the pendulum. This is what we call a simple pendulum. We're assuming the string is plenty strong to support it, but that the string has no significant mass. Now obviously the more mass we suspend over here, and of course then we get a weight. A suspended weight over here. Now, the more mass we have, the greater the weight here. If this is a good pulley, and let's kind of draw a pulley support here. Okay, again, the more mass we have here, the more tension we'll have in the string that suspends the mass. And that string goes over what we assume to be light frictionless pulley to the pendulum, and there'll be a tension in the string that pulls the mass up, and the same tension in the other end of the string that pulls the pendulum out this way. And if the pendulum is suspended in an equilibrium situation, not at its equilibrium position, but suspended here without accelerating, then the tension in the string will be equal to the suspended weight, again to the extent that the pulley is frictionless. We ask what forces are acting on the mass of the pendulum. We're going to construct a free body diagram for the pendulum mass, but let's ask right now what forces are acting. Okay, so what's one force? Well, this thread, or this string that's supporting the pendulum, has a tension, and that tension acts in the direction of the string. This string, the string that suspends the mass and is attached to the pendulum, excuse me, also has a tension. And we also have gravity pulling down on the pendulum mass, so that there's the weight of the pendulum pulling straight down. So we sketch the free body diagram. We have the tension in the string, which is pretty close to being equal to the suspended weight. So I'll label that vector weight suspended. We have the tension in the string, the pulley, the pendulum string. Which I'll just call T. Now, I put an arrow over T to indicate that it's a vector. I didn't put an arrow over the suspended weight because, of course, that weight force is straight down, but because of the pulley and so forth, the suspended weight, the magnitude of the force, the magnitude of the tension force is equal to the suspended weight, and this only indicates the magnitude of this force. We could, if we want to put an XY coordinate system on it, specify that as weight suspended times I, where the x-axis is to the right. We might not want the x-axis to be to the right, so we want to maybe hesitate a little bit to do that, but I'll go ahead and do it here. Okay, the weight force, weight of the pendulum, which I'll simply call W, is straight down. So we have the three forces: the tension force in the spring, in the horizontal string, the tension force in the pendulum string, and the force exerted by the gravitational field of the Earth on the mass, or the force exerted on the mass by the mutual gravitational force between the mass and the Earth. When I labeled this vector W suspended times I implicitly indicated that the x-axis is going to go this way, and of course then the y-axis will be here. And we note that both the weight and the tension force in the horizontal string are parallel to coordinate axes: the weight to the y-axis, the tension force in the horizontal string to the x-axis. If we want to analyze this system, well, what do we know about the system? We know that the pendulum mass is hanging in equilibrium. We just saw that. So this is an equilibrium situation. We know that these three vectors have to add up to 0. So we're going to analyze the system a little bit more. The first thing we want to do is we want to get all the vectors into their components parallel to the x and y axes. These two vectors are already in their components. Tension force, we're going to have a force Ty and a force Tx, the components Ty and Tx, and now the tension force is going to disappear. Now what's the condition of equilibrium? Sum of the forces in the x direction has to be 0. Sum of the forces in the y direction has to be 0. Which means that negative t sub x, negative magnitude of t sub x in this case, plus the magnitude of the suspended weight has to be 0. It takes care of the x. And in the y system, Ty minus W has to equal 0. I could put arrows over Ty and W and then put absolute value signs around them, but we're just saying that the magnitude of Ty minus the magnitude of W equals 0 because Ty is in the positive y direction, W is in the negative y direction. So officially we have Ty times I times Ty times J minus W times J equal to 0, but that simply comes out this way. We'll go on with this. Hang on a second. Now we have the equations that describe the equilibrium. We'll come back to those. We're going to make an observation. We have a right triangle here because, of course, the vertical line down to the equilibrium position makes a right angle with the horizontal line. So this is a right angle. And the tension force is in the same direction as the length vector. So we have a right triangle here. We have a right angle here clearly, and this angle has to be the same as this angle. So drawing that up here, we see that this angle, excuse me, has to equal this angle simply because the tension force has to act along the direction of a string. The tension force exerted by a string has to act parallel to the string. From this, it follows that the tension, well, I'm sorry, this statement says the tension's parallel to the string, so the triangles are similar. Okay, so if the triangles are similar, what do we say? That this side over this side is equal to this side over this side. We can write that. We have Tx is the length of this side, T is the length of this side. Tx over T equals x over L. And from that it follows, of course, that T sub x, the x component of the tension, is equal to the tension times x over L. Now, another thing, if x over L is small, then the tension vector is close to the y-axis, and there's not much difference between the length of the tension vector and the length of its y component. I think I might have had my head in the way there. This vector is going to be very close to the y-axis if x is very much smaller than L, because, of course, if x is a lot smaller than L, this angle is such that the string is fairly close to vertical. Okay, so the closer the string is to vertical, the closer the y component of the tension is to the tension. And of course, the y component of the tension is equal to the weight of the pendulum. So we conclude that the tension is approximately equal to the y component if x over L is small, and the y component is equal to W, and from that it follows that the x component of the tension is W times x over L, just replacing the T here with the W, which can be written as W over L multiplied by x. Now if we combine that with this, we come up with the conclusion that we can actually test with a real pendulum. From this condition of equilibrium, we conclude very easily that Tx has to be equal to the suspended weight. So Tx is equal to the suspended weight. Tx equals W over L times x, which we just found here. Put these together and we find that the suspended weight divided by the weight is x divided by L. Meaning that if x is, let's say, 3% of L, then the suspended weight here that will hold the pendulum at that position is going to be 3% of W. So that's kind of a profound observation, and we can actually test that with the actual pendulum simply by looking at the displacement x, dividing that by the distance to the ceiling, and then we know how much weight is suspended. We know from the x over L ratio what this ratio has to be, so we could determine W, the weight of the pendulum. If the weight suspended is expressed in domino weights, in paper clip weights, then we know how many paper clips should equal the weight of the pendulum.